All right, so picking up with transformations. Okay, yesterday we talked about moving these things left, right, up, down, and reflecting. Today I want to talk about the stretching aspect of them. And the first thing is to talk about the vertical stretch. So when we talk about stretching, there's two things that can happen. We can actually make it taller. Okay, and that's what most people think about when they hear the word stretch. We can also compress it. Okay, and you're going to hear kind of different terminology. You'll hear them say stretch vertically. They might say shrink vertically, compress vertically, that kind of thing. Using just synonyms for stretch. Okay. Yes.
Did you play in the alumni game?
No, I did not.
Why?
I didn't have time. All right, so it's the graph y equals c f of x. Okay, c f x. So what they're doing is taking c, which is what we call a scalar multiplier. Okay, just a fancy word for saying it's a number out in front that you're going to multiply everything by, and it's going to impact your y's. And it's going to multiply your y's by whatever that amount is. Okay, so if you remember back to geometry, we did dilations, right? And a dilation is simply an enlargement or a reduction of a pre-image. That is all these are. That's all we're talking about with stretches. Now, when we did it in geometry, we did dilation, we did it to both the x and the y values, meaning that we just took our dilation factor, our scale factor, we multiplied all your x's by that amount and all your y's, right? Okay. Well, when we were talking about functions, we like to be more kind of specific and say, I just want to multiply my x's by this amount, or I just want to multiply my y's by this amount. I don't want to do it to both. Okay? So this allows us to multiply just the y's by some amount. And the behavior then, or the product of that for our graph is that our graph gets stretched vertically, gets taller in the vertical direction. Okay. Now that's if c is greater than 1. Okay, because if c is greater than 1, you're making your y values larger numbers if they are greater than 1. Okay, or you're making them smaller values if they are between 0 and 1. Now, if your constant c, your scalar multiplier, is between 0 and 1, so for instance, like take the point 4, 16 off of your quadratic function, 4, 16. So that would be a point off of y equals x squared, right? Okay, well, if I make it y equals 1/2 x squared, now that 4, 16 just turned into 4, 8. So we take our 16 and we multiply it by 1/2. Does that make sense?
Yeah.
So what's happening is that we're taking our parent function ordered pairs, and we're taking the y values and multiplying them by whatever that multiplier is, whatever c is. Well, if c is bigger than 1, it's going to make those y values grow. If c is between 0 and 1, it's going to make those y values shrink. And then, graphically, we get that vertical stretch or that vertical compression. So, I kind of want to demonstrate this real quick with GeoGebra. Last period, my GeoGebra was, well, the pre-made ones that I had that had the function that you type in, made just user-friendly. Those are still available to you, but I think I had my OneNote running, I had GeoGebra running, I've got this pen tool running, and just I think GeoGebra is the thing that lost some memory, and it just kept freezing on me. So I gotta have all those other things open. So let's just see if this will work. If I have f of x, let's just say x squared. Okay, so we got some points on there that we're aware of: 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. We've got those ordered pairs. Okay, let's put in the function. I think I can do it this way. It might make more sense. Let's just go a times, or let's go C, because that's what our definition was using, C times f of x. And it allows me to create this slider for C. Okay? Well, if I do this, go to C right now, that C is 1, so these things are the same. So if C becomes bigger than 0, we get that curve to happen. Okay? Now, what I want you guys to realize here is that this point here correlates now when C is, let's make it 2, to that point there. So F and H match up. Does that make sense? So let's call that, just to make it a little bit easier to see, let's call this F prime. Okay? I'll put C in here. We'll make this C prime. Let's put that point and that point, call this one E prime and B prime. I'll show you. All right, so as we see this, okay, you see if we look at E and B, as I start to move C, do you see how they just get moved straight up? Okay, and they're getting moved straight up right now by a factor of 2.1. Okay, if I make that factor go to 3, now they go to 3. Okay, so we have then this order pair is at 1, 3. Okay, let's look at these two, F and F prime. If I look at their coordinates, do you see how, so this F is off my parent function, right? Negative 2, 4 on 3x squared. It's still negative 2, comma, now it's 4 times 3, right? 3 being that multiplier. That kind of makes sense to everybody? Okay. So now the question is, well, what happens when this thing is between 0 and 1? Okay, so when C is between 0 and 1, so we'll put it back at 1, and that gives me that function, right? So now we see, for instance, F and F prime being the same point. Now if I start to make that multiplier between 0 and 1, my hopes are you see it that makes that 4, multiply 4 by 0.7, and you get 2.8. Take 4 and multiply it by 1/2, you get this 2 here. Multiply by 0.2, and you get this 0.8. Does that make sense to everybody? Okay. Now you're asking, well, what happens when this becomes negative? Well, what does a negative do if I just did this and I made this number out here, if I made C negative, what does negatives do out in front in regards to transformations? Flip it over the axis. Which one? The x-axis. So now we see that. So now we're kind of coupling two transformations there. We're doing a shrink, a vertical shrink, and following that then by a reflection as well. Okay, so you can like I said, you can couple these things if you need to. Now, if let's see, here's my thought on this. I didn't want to get rid of that, but I wanted to go like that. Can you guys visualize this is how I think about a stretching. This is why they call it a stretch. Think about putting your hands at D and G. Okay? Grab that graph and pull your hands straight up. Does that start to... Oh, I got to change this. 1, 2, 10. All right, so if I put my hands at G and D and pull straight up, is that what happens to that graph when I do that? Yes. That makes sense? Now, the idea is that I've got kind of like a nail at point A down here, and that's not going to move. That point is staying 0, 0. And the reason I can put a nail there is because no matter what I multiply 0 by, I get what? A 0. So that is going to stay put. But as I pull up on G and D, that thing is going to be a stretch, and the graph looks like it's getting skinnier, right? Okay. Well, if I put my hands on G and D and now push down, okay, this point's going to stay there. Okay. And what I like to think about, if you guys had like a thin piece of like aluminum, or just a real narrow ribbon of metal, and you put a bend in it like this, and you put your hands at G and D, and then push down on G and D. Okay. So again, that would mean this has got to go between 0 and 1. But if you push down on G and D, okay, that piece of metal ribbon or whatever is going to try to maintain its shape. Does that make sense? Okay. So what's going to happen is it's going to kind of bow out. All right. And that is called a vertical compression. All right. Questions on that? Yes. So you're going to hear them say vertical shrink or vertical compression, and those are the same thing. If we can do, so this is the thing that we've been talking about. If we can do something to the y values, we should also be able to do something to the x values, right? That's what we did yesterday. We shifted graphs up and down, and that ultimately impacted the y values. And then we said, well, let's impact the x values. Let's move it left and right. Okay. Then we did a reflection across the x-axis with the y values. And so let's do a reflection across the y-axis and impact those values. Okay, so an x-axis reflection impacted the y's, and a y-axis reflection impacted the x's. So right now we just did a stretch that impacts only the y's, right? Well, let's do a stretch that impacts the x's. Okay, and this is going to then produce what we call a horizontal compression or horizontal stretch. Okay, so this is the rule right here. Okay, as I'm going through these slides, guys, these PowerPoints are, when I first kind of combine all this information, I made them so that when you read through them on your own, you're not missing anything. Does that make sense? So I'm not going to sit down and read every one of them to you. I'm going to make sure that we talk about the key information and all that stuff that I skip over. We do talk about. I'm just not going to make you write them down. Okay. So now what we're going to do is we're going to take our f of x, our function, and the notation is a little bit odd here, but right here it's saying now instead of multiplying previously with the vertical stretch, we had the c out front, right? And that says you're going to take your y values and you're going to multiply them by c, or they're going to be generated by taking your function and multiplying by c. Here it's saying to get your y values, you first have to multiply your x by c. So if we do something to x first and then run it through our function, that's going to impact the horizontal aspect of the graph. Okay. So what that would look like if I gave you a specific function is something like, if I have like f of x equals, let's just say, x squared, then this here, what they're saying is that your f of x is going to be like 2x squared like that. Okay? Which if we did a little bit of algebra, which you guys can do here, that'd give you 4x squared, wouldn't it? Instead of just 1x squared. So what's going on then is that we're saying my overall function is the power of 2 function. Okay? The quadratic function. But before I evaluate using that square, I'm going to take whatever independent variable I want. Maybe x is going to be 1. And I double it before I square that. Does that make sense? If x is 2, I double it before I square it. If x is 3, I double it before I square it. And that process of taking your independent variable and applying this multiple to it first is actually going to create what visually looks like a compression. Looks like your x's get closer to one another. Okay? So when this number here is greater than 1, when your C is greater than 1, okay, and this is because the horizontal relationships are kind of the inverse of what we think should happen, or counterintuitive is the word I used yesterday, to what we think should happen. Okay? When I multiply something, I think it should get bigger, right? And when I think bigger, I'm probably thinking it should stretch. Okay? But when you do it to the x's, it's going to actually create a compression. When your multiplier for your x's is bigger than 1, it creates a compression, a horizontal compression. Okay? I like to look at this kind of parent function here. They're giving me this blue one as the parent function. And if I put my hands right there, and obviously I know at that point 0, 0 is staying put. If I put my hands on those x's and I push my hands together, kind of like an accordion here, I'm going to eventually generate that red one, right? Okay. If C is between 0 and 1, so if C is a fraction between 0 and 1, then it's going to be putting my hands on those x's, and I pull my hands away from one another, and it's going to stretch that graph out. Okay. The one thing you got to pay attention to is not that C is a fraction. When I say 0 to 1, a lot of people think, oh, it's a fraction. Okay. Well, 9/5 is a fraction, right? Is 9/5 between 0 and 1? No. So that would produce a compression, right? So make sure you're not looking for just fractions, but you're looking for numbers between 0 and 1. Okay. That being said, let's look at this stuff with a graph. And this is going to be kind of a pain in the butt, okay? Because when we deal with, let's just say I start with f of x equals x squared, okay? And now I want f of 2x, okay? Does that green curve look, now just bear with me here, does it look like you have taken maybe that point right there and that point right there, put your hands there, and push that way? Yeah. Is that the way I gave you the green curve? Okay. So that'd be a horizontal compression, right? Does it also look like maybe you could have taken that point and pulled them straight up like we did previously, and at some point still get that green curve? Okay. Why? Why does it look that way? Do the algebra here. What do you get when you do that algebra? 4x squared. Isn't 4x squared taking x squared and stretching it vertically by 4? Yeah. Does that make sense? Okay. So when we have 2x, that quantity squared, we can visualize that as a horizontal compression. Okay. But if I actually do the algebra to that function, I also see that horizontal compression, which is a factor of 2, is analogous to a vertical stretch with a factor of 4. Does that make sense? So here's the thing with power functions, and with a lot of our functions actually, it's going to be hard for us to see graphically. They're not going to give you a graph and say, tell me what the stretch was, or tell me what the compression was, okay? Because the vertical stretch might look like a horizontal compression. Does that make sense? Or a vertical compression might look like a horizontal stretch. Is everybody kind of on the same page with me as that? That's hard to visually recognize. If I were to give you this right here and I asked you, what's going on? There'd be two answers to that. You can either say it's a horizontal compression of 2 or it's a vertical stretch of 4. And because of that ambiguity, a lot of times they refrain from giving those types of questions. I think on the homework, for the most part, they'll give you a function like this and ask you what is happening. Okay? Is it a vertical stretch? Is it a horizontal stretch? Because you should be able to tell from the function. Okay? But if I cover up the function and look at just the graph, that's going to be difficult to kind of narrow it down to the one that they are interested in. Okay? It will be something, guys, that is a lot easier to determine when we talk in trigonometry. Okay, so here's the thing. These principles right now that we're talking about, Now, I just want to open your eyes to this because I want to make sure that we fully dedicate ourselves to this, Chuck, and make sure that we fully understand this by hopefully the end of this week, because every chapter is going to come back to transformations. Every course that you take here on out at some point is going to have an aspect of transformations. Okay? We get to trigonometry. The number one thing we'll do in trigonometry is we'll say, okay, I'm going to look at this function here, sine of x. Okay? You guys that are in physics will see this eventually with light waves, sound waves, that kind of stuff, electromagnetic waves. But that's our sine function. That's what we call that a sinusoidal. Now your cosine function looks very similar. Okay? So cosine function looks like this. Okay? Are those very similar? Okay, now what I'm going to do, just to prove to you how important this stuff is, I'm going to take this cosine function and I'm going to subtract 90 degrees from it. Okay? And when I subtract 90 degrees from it, it put it right on top of the other one, right? Yeah. So what this tells me, and maybe we can see it a little bit better if I do it this way. Let's put a slider together here of A, and I want to go from 0 to 90.
Why'd you put 90 degrees pi over 2?
That's what it is. So if I take this and I slide this, would you guys agree that as I start subtracting amounts from that, I will eventually get that blue one to turn on to that red one?
Yeah.
Okay. So the pi over 2, 90 degrees, that's a radian. A radian is, for every 180 degrees, it's equal to pi radians. And we'll talk about that when we get to that. Yes, it is. It's exactly how math works. So when we do distance, you do it in what? Like, what's your number one unit for distance?
Feet.
Okay, you want to do feet? Okay, well, everybody in Canada that is French uses meters, right?
Yeah.
Okay. Everybody else in the world, there's 3 countries in the world that use feet. We're one of them. Okay. Everybody else uses the metric system, right?
Yep.
Okay. So we understand that there's 2 units for distance, right?
Yeah.
Well, what is the number one measurement you use for angle measurements? Degrees. There's another one. There's a better one. It's called radians. Okay? But it's the same idea as how we use feet because we're accustomed to it, or miles because we're accustomed to it. Everybody else uses kilometers. We're accustomed to degrees, but radians are more applicable.
Wait, what are the other 2?
No, they're in Europe. I forget what they are. Yes, pirates is. We're just gonna stop. It doesn't right now make sense to talk about that because we don't have time to. But what I want you to see is that a horizontal translation? When I take that blue one and start moving it, is it moving horizontally? Does that make sense? Okay. Well, this is going to be a very important aspect for us. What's going on? Okay. This is going to be a very important aspect for us in trigonometry. So horizontal translation is going to be useful in trigonometry. Okay. You guys know what amps are. Let's talk about so that sound travels in what we call compression waves, but they can be modeled using these types of things. And when we talk about amps, like an amplifier for like music, right? That's what I'm talking about here. Okay. Well, if I put a 3 out front, okay, that 3 is called the amplitude of our graph. But it makes the y values larger. Does that make sense? Okay. So that's a vertical stretch, is it not? Does that make sense, everybody? Okay. So the whole reason I'm talking about this sine function is because these are called periodic functions, meaning they do the same thing over and over and over again forever. Okay. This thing, no matter how far out I move, is doing the same thing, right? Okay. Now, the reason I want to talk about this is because in trig, it will then make more sense to put maybe a 2 here and see what happens. Do you see there, if I put my hands on the outsides of the red curve and push them together like an accordion, and that's like a metal ribbon that will move, okay? But try to keep its form. If I push on my hands, you see how that thing's going to kind of create or turn into that green function? Does that make sense? Okay? That is much easier with that type of function to realize that sine of 2x, because of where that 2 is it providing us a horizontal compression. Okay? So in our talks or discussions about horizontal compressions and stretches, usually the best time to talk about those is when we work inside trigonometric functions, because of their periodic behavior, we can see the stretch or compression a little bit easier. Okay? Your floor function or your greatest integer function is another one that we can use to demonstrate horizontal stretches and compressions, but these are the best. Okay? Yes? Next week. We'll talk about it at the end. All right. All right, let's do some examples.
Did we done for the other class? Are we ahead of schedule?
No? If I gave you the function, let's go, let's say f of x is equal to, let's go negative 2x plus 3 squared minus 1. So what I want to do with this is I want to, on tests and quizzes and some of your homework, our goal is to be able to go through this thing and determine several things. What are all the transformations that are taking place? Okay. On tests and quizzes, I'll kind of list them down the side here. I'll ask, is there, and you don't have to write these right now, I'll say, is there a horizontal translation?
Yeah.
Okay, is there a vertical translation? So I'll list all these things, right? I think when we're doing these together, it makes sense to just kind of talk about what, just going left to right, what does this negative do if it's out in front of the whole thing? X-axis reflection. Okay. What does this multiple of 2 do? Stretch by 2.
Did we just ignore the negative sign? Like after we already...
We just identified it. Stretch by 2, but is that vertical or horizontal?
Horizontal. Vertical.
Vertical.
What?
Because remember, what's getting impacted? Am I doing anything to the x? No. Okay? So that 2 is being applied to the whole thing. Now, this is the reason why we have some dependence on reflections and shifting, is because this reflection, if I were to multiply all this out and do the algebra that is here, because we can, right? We can FOIL this, we can distribute the negative 2 and all that kind of stuff, combine like terms. This negative is only getting applied to this stuff here, right? So this reflection is getting applied to this stuff. It's not getting applied to this negative 1. So that's why yesterday at the end of class I showed you that blue box on my website that said do H, horizontal shifts, first, do S, which would be stretches, second, do reflections, third, and do your vertical translations last. Okay? And it's because of the algebra here with distributing that negative. What does this plus 3 do for us?
Left 3.
Left 3.
Let's go.
And what does this negative 1 do for us? Down 1. Okay. Now, what was the parent function? Good. The parent function is f of x equals x squared. And everything that we do then will take and move the points that we are aware of on x squared using those transformations. So, give me some points that you know off of x squared.
749.
Why do you always use that one? Okay. So 0, 0.
Wait.
negative 1, 1, negative 2, 4, 1, 1, 2, 4. And if you want to use 749, use 749. But here's my fault. The reason I'm doing this is I want to graph this thing in a minute. I don't want to graph 749. Do you want to make a graph out of 49?
I want to make a graph of 7.
All right, so what we're going to do, if those are our parent function points. Okay? We're going to apply all these transformations to them. Okay? Now, here's the thing. I want to go in this order. Horizontal translations, stretches, reflections, and then vertical translation. Okay? As you get better at these, okay, you might be able to do 3 or 4 at the same time. Okay? I think that's a challenge. Sometimes it gets yourself in a little bit of hot water sometimes if you do that. So initially I'm going to be deliberate. I'm going to go one at a time. Okay? So do we have a horizontal translation?
Yes.
Yes. So it's going to take these ordered pairs and move them all left 3 units, right? So if I go left 3 units, what is this point going to become? Negative 3, 0. What is this point going to become? Negative 4, 1. So, here's my question. What are you really doing? When you move these left, you're doing what to the x's? Subtracting 3. So this becomes negative 5, 4. This becomes negative 2, 1. This becomes negative 1, 4. This one becomes positive 4, 49. Does that make sense?
Sure.
Okay. Just moving left says you are going to remove a value from x. So subtract 3 to make sure all those are right. Now here's what would kind of stink if one of those was wrong, and we do the other 3 or 4 transformations here, then we're going to be wrong at the end, right? So double check all your work. We should be good there. Now, so that was the horizontal. We did the H. Now I'm going to do the stretch. Okay, so the stretch is by how much?
2.
Vertical stretch by 2. Okay, and when I do a vertical stretch, what coordinate is getting impacted? The y is getting impacted. So the x's don't change, right? So I'm going to rewrite these x's. And now these y's are going to go and double, right? Okay. So now I get 0 there. I'll get 2 there, 8 here, 2 there, 8 there, and 98 there. Okay. So we did the stretch. Now, we've got a reflection, right? Now, do I have an x-axis or a y-axis reflection? X-axis. So when I reflect across the x-axis, which values are altered? The y's. Okay? So they're altered by just the negative, right? So here's kind of my argument is that when you get better at these, you can save yourself a little bit of time. Come on. There we go. You can save yourself a little bit of time and do these reflections and maybe the scalar multipliers at the same time. So all I've got to do is go through here and negate all of these, right? Yeah. So negative 2, negative 8, negative 2, negative 8, negative 98. And when you get really good at these, you might have known that, well, after I negate them all, I can subtract 1 from them all, right? Because subtracting 1 is going to be the vertical translation. That's the last thing we do. So here's the argument. Well, we'll say that when we're done. So I'm going to go -3, subtract 1 from the y. -4, subtract 1 from the y. -5, subtract 1 from the y. -2, subtract 1 from the y. -1, subtract 1 from the y. 4, subtract 1 from the y. Okay, so that would be the vertical translation, which is down 1. Okay, here's my question. If you would have moved these down first, if you would have moved that down first, so that would have been making that -3, -1, right? And then reflected, would you have gotten that point? No. If you would have moved that down once, or by 1 first, and then multiplied by -1, would you have gotten that point? No. So do you see how the order that you do your transformations is important? Okay? And the idea, and I'll probably have to show this tomorrow, the idea is when you do a vertical translation, you have to do it. If you do the translation before a reflection, then you're not going to reflect over the x-axis anymore. You're going to reflect over a shifted x-axis. Okay? And I'll show that again tomorrow. I'll visually show that to you in a graph tomorrow. But now we should be able to plot these points. So I'm going to go, and you can do this just to save time. I'm going to do it on GeoGebra. Do it on Desmos. Do it wherever you want to do it. A lot of times maybe you're doing it on a graph paper, on a test or a quiz. But we're going to take, I like using these things because once I'm done, I can then type in my function and see if my function passes through these points. So I've got -3, -1. We've got -4, -3. We've got -5, -9. -2, -3. -1, -9. And 4, -99. And when we look at that graph looks like if I put a smooth curve through it, it'd be parabolic. Okay, so I'm going to do that. Our function was -2x plus 3 squared minus 1. Does that blue curve go through those points? Yeah, and you really want me to go down there, aren't you? Okay. So that, I think, is the best technique for doing this type of thing. Now, some people are fans of, instead of writing the list that we just made with the transformations just to the order pairs, they like to do it graphically. They like to see it in front of them. So what I'm going to show you here, hopefully you realize, is exactly the same thing we just did. But they want to see it this way. They want to go, and maybe I just use, I might not even use these order pairs up there. No, I'm not going to use those two. So let's just say that we do our transformations with those three. So this should be A prime. This one will be B prime, and this one will be D prime. Okay, so those were for my parent function, right? Well, if I go to this function over here, so it said you are going to move 3 to the left. So what they say is, okay, I want to take this point, and I'm going to move it 3 units to the left. And this is really, this gets to be problematic a lot of times if you're using one color. Okay, so I like to bounce back and forth between different colors here. So move this 3 units to the left. So that's going to put it right there, right? Move this one 3 units to the left. So it puts it right there. Move this one 3 units to the left. So it puts it right there, right? So that took care of that. Okay, now I want the 2. So the 2 is going to stretch them. So this one here, so I'll do these in blue then. That one's not going to get stretched. The y value is 0, right? Here the y value is 1, so it's going to get stretched to 2. Here's the y value of 1, it gets stretched to 2. I hope you see now the issue that if I'm using one color, I'd have a bunch of black dots up there and I can't keep track of which ones are which, right? Okay, so now I'm working on the blue ones and I've done the 2. Now I need to reflect them, right? So if I'm reflecting them, I'm going to use yellow here. reflect this one, and it's going to go right there. You guys can't see yellow very well. Okay. So if I reflect that one, reflect that blue one, it goes there. If I reflect this blue one, it goes there, right? Well, this one's on the x-axis, so when I reflect it, it stays there, right? So I did that. Now this -1 was here, right? So now it says drop each of those 1 unit. And does that become then the points that are on that curve? Okay. We do have a little bit of time here. Let's okay, let's do some more. You guys had some homework questions.
Yeah. Let me have my computer real quick. I had to send like 3 emails and ask him 4 times for an email.
All right, cool. So what was your question, Cole?
I don't have a question. Yeah, we smell like salami, so.
You make that sound like it's a bad thing. All right.
Okay, so what is average rate of change?
Slow.
So like for number 1, how do you get to like the last part of it? It's like f of whatever minus f of whatever equals like I just do the smaller one, that is the big one. I did the subtraction, but somehow like.
What's it say? Read the question to me.
F of 4 equals 2, and F of 2 equals 7, and then F of 4 minus F of 2 equals, and then I got that part wrong. Mr. Baker, can you help me out?
So this question here?
Yeah, that's what I'm doing, dude. No, mine's number 1.
This is number 1.
Yeah, that's my number 1 too.
We're talking about Peyton, we talking about the 2.5 average rate of change assignment?
No, this is 1 to 9.
No, 2.3.
Oh, okay.
Wait, 1 to 9?
2.3. Been open for about a week now.
Yeah.
This one?
Yeah.
All right, so it says, to find a function value f of s in the graph, we find the height of the function above the x-axis at x equals a, right? So that's saying basically if I want to find the height of the graph at x being 2, that value, so that would be 2, this here would be f of a, which would be f of 2. Does that make sense? If a was 2. Is that cool? All right, so then we see that f of 4, so f of 4 would be here, it has a height of 2, right? Okay. F of 3, right here, right, has a height of 4. So we're getting the 4. Says the net change. What's net change? Like if so net is just, when we say net change, we're just talking about the change from one to the other, the difference between one and the other. Okay? The net change, which says x is 3 and x is 4. So you are going to look at x being 4. You always go to the one that's to the right. So x to the 4th, or x sub 4, sorry, x equaling 4 is to the right of x equaling 3, right? So I'm going to go up to 3, or this is up to 2, sorry. So f of 4 is 2, f of 3 is 4, right? And those are the values we already found. So then you do 4 minus, so f of 4 minus f of 3. Does that make sense? So it's asking you to take the f of 4 value minus the f of 3 value. Okay? Well, f of 4, so they were walking you through this. F of 4 was 2 minus f of 3, we said was 4, and that gives me -2. So the net change Now, the reason I want to go with an x value that is bigger, so I went the full f of 4 first minus f of 3, is so I get the right decrease of -2. If I flip-flop it, I get 2, right? And that would show me increase on the graph, but I want to show decrease on the graph. So net change is just it's y2 minus y1. Does that make sense? In my slope formula, it's the numerator. Okay? The denominator then provides me what I divide by, so when I divide by that denominator, then I get the average change. So the net change is the change over the entire distance. Okay? The average change is then basically seeing what that blocks up to or chunks up to kind of in a unit rate. Okay? With the denominator being what this is how much I drop every 1 unit. Huh? Draw what? This? It was like that. Look at this big. So another question. Other questions? Same assignment?
Balance your nugget all those right and done.
All right, so the solution of the inequality f of x is greater than or equal to 0. So that is so this is 0, right? Right across. I don't use this one enough to remember to change the size. So that would be equaling 0, right? Okay. So this is saying for your function, when are the y values of your function above that y value? Well, aren't these the ones that are above the y value? Does that make sense? So then the answer then is an interval of x's. So between x being that value right there, which is 1, and that value there being 7, this curve is above 0 from 1 to 7. And now, because we got equality there, we've got our brackets here.
Yes. That's how you move it.